All right. This is example problem unit D0, page 5. This is a fire extinguisher. Fire extinguisher is essentially a bottle which contains fire extinguishing fluid inside. I'm not exactly sure what it is, but there's some kind of fluid inside of it. So fluid flows from the fire extinguisher tank. Let's discuss the differences between dB cis dt and dB Cv dt if B represent mass. So this is the time equal to 0 of fire extinguisher. So at the time equal to 0, you're going to open the valve, so let the fluid inside of this tank shoots out and let it go. Okay? So I want to analyze this by using two different kind of methods. One is analysis using the system, which is essentially purely Lagrangian method. Okay? And also at the same time, we can do analysis using control volume, which is purely Eulerian method. So let's compare against those two. So first of all, let's begin with Lagrangian-based analysis here. So this is fire extinguisher. This is a time t equal to 0. So this is right before you open the valve. So let's consider the system. System is a fluid. Fluid is a system. Okay. So what is the fluid? Fluid is made up by small tiny particle of fluid. Okay. So this is the tank, contains fire extinguisher fluid inside. So I'm going to illustrate what's the situation. So those are the particle of fire extinguisher fluid. I don't know how many particles in it, but it must be a lot of particles. So lots of fire extinguisher fluid particles contained within this tank. And just keep doing it. So those are the particles of fire extinguisher. Obviously a lot more than that, more tightly packed probably. So this represents the system. System is essentially collection of all the particles of fire extinguisher. Extinguisher fluid. I can't spell obviously. Fire extinguisher fluid. So particles fairly tightly packed inside of this tank. If you pick up every single particle, add them together, it's going to be called fluid fire extinguisher. It's a system. Okay? So system approach is you're going to keep track of the property of each particle. That's the Lagrangian. So what happens? Right at the time equal to 0, you open the valve, let those particles move out. So particles start shooting out. As soon as you open the valve, just like that. And I bet still lots of particle remains inside. Okay, right after you open the valve, right? Okay. So from the system perspective, Lagrangian. So this is the situation at right after you open the valve, t equal to some positive body. So right after you open the valve, some of the particles starts to go out of this tank, and some of them still remain. But as time goes by, probably everything goes out. Okay? So discussion about this. Okay, let B equal to mass. So let's discuss about dm says dt. dm sys dt, mathematically speaking, what is this? This is how much mass of the system change over time. Okay. Now, if we keep track of the system approach, this really is capital dm sys dt. The reason why this must be capital is the change of the property here depends on two things. Two things means that the property of each individual particle depends on, number one, its location. If this particle originally sitting here, now it's here, does that make the property of this particle change? Sometimes, yeah. Okay, sometimes, yeah, sure. So you have to keep track of that within. And also, this is a time equal to 0, this is time equal to sometime later. If you look at the same location here, does that change that location's particle's property? Yeah, I guess so, sometimes. So this includes two things, time rate of change and position rate of change. This is called substantial rate of change, total. Total rate of change. So under the Lagrangian or system approach, you have to keep track of total rate of change of the system property. So that means every single particle, as it moves, as the time goes by, how the property of each particle change. That's this. So you have to keep track of total rate of change. Okay? So what is your conclusion in this case? dm sys dt, what's that? One of the significant importance of this Lagrangian approach is Lagrangian approach is going to usually determine your fundamental principle of conservations. dm sys dt, okay? So now the property we are talking about is mass. So let's see, this is a small tiny particle of fire extinguisher fluid. This particle's mass is, I don't know, 0.00001 gram or something. This one moved out to here. What is the mass of that particle? Your answer is, well, it's the same, isn't it? Mass doesn't change. Yeah, mass doesn't change. It's the same amount of mass. So what's the conclusion? How does the mass change over time, over position? It doesn't change. Mass doesn't change. That's what I'm saying. Have you ever heard of it? This is called conservation mass principle. This is a principle. We are going to talk about three different kinds of conservation principles in fluid mechanics. Conservation mass, which is this, conservation of linear momentum, and conservation of energy. This is one of them. So this is Lagrangian approach. Oh, that's really nice, isn't it? Yes, that's great. Does it solve anything, practically speaking? No. This is a fundamental principle. Can we, engineers, pick up this equation, apply it to solve something? For example, I'm kind of curious, how long does it take to empty out this fire extinguisher? I want to know that. Can we find out from this equation? The answer is heck no. You can never do that. Oh, how practical this thing is. This is very accurate, but nothing near practical. This is the equation applicable to every single particle, which is true, but how practical is that in terms of real engineering solution? Well, none. Okay. So having said that, I want to talk about Eulerian approach. So Eulerian approach is control volume approach. Okay, so let me do that. So let me just assume this bottle is a control volume. So I'm going to define a control volume being arbitrarily the chosen volume in space I'm interested to analyze. This is control volume. Control volume, this is fixed in space. So this control volume does not change or deform or move over time. So at the time t equal to 0, at the time t is more than 0, control volume is the same. So you have the exact same control volume. Okay? Alright. So once again, let V is equal to mass. Okay? So what I'm interested in is dmc v dt. Oh, it's a slightly different meaning here. This is the change of mass with respect to time of the system in which we do know it's 0. It's a Lagrangian approach. Now this is a slightly different approach. We define the control volume fixed in space. Then we put our eyes only on that control volume. Now once you define the control volume, you're going to automatically define the control surface. This is control surface outflow. So across this surface, something flows out. Okay? Control surface outflow. Everywhere else is fixed control surface which have nothing flow across. Okay. So let's take a look at the mcv dt. So this is essentially how much mass changes within the control volume over time. This is inevitably, meaning-wise, this is partial. Okay? How come this is partial? Mass depends on two things, like I said. Well, actually, not the mass. Property. Change of property depends on two things. Property change happens over time for a fixed location, or property change happens over a different location. We are not going to look at the different location. We are only fixing the property, in this case mass, within this control volume only over time. So this is a partial derivative. We do know the property depends on two things, time and space, but we're not going to talk about space change. Only time rate of change within the control volume. So as the time goes by, how much mass change happens within the control volume? What do you think? Well, apparently, within the control volume, mass keeps changing, right? At the time equal to 0, right before you open the valve, within the control volume, fire extinguisher fluid is filled up. But when you open up the valve, let fluid escape across this control surface. As the time goes by, the mass within the control volume decreases and decreases and decreases and becomes 0 later on. So this is obviously some kind of negative value. It's not going to be 0. So conclusion, dmc v dt is some kind of negative value. And then problem. How much negative value? I don't know. All I can say is, if I define control volume like this, I can say, oh, mass decreases from the tank. Oh, how much rate? I don't know. So this is typical Eulerian. which is engineering approach. So engineers want to say something practical. This is fairly practical. You can say, well, the mass decreases from the tank over time. Yeah, that's more practical and useful information, but it's not accurate. This one, Lagrangian, typically scientific, mathematical approach. Based on this approach, well, if you keep your eye on this small tiny particle, this particle's mass never changes no matter where you go. Oh, that's so nice, it's always true, but how practical is that? Nothing practical. This is super accurate, but you cannot really use it for something real. This is something real, but it's not accurate. Oh my goodness, we need something in between, right? Okay, so we want to take a look at something which is, well, building bridge between here to here. So, basic principle developed at the Lagrangian. If you go through Reynolds transport theorem, now there becomes some kind of governing equation. It is going to find out how much actual value here so that you can solve the problem. Reynolds transport theorem being the bridge between Lagrangian to Orion. So we are going to discuss about that in this unit D0. Okay? Let's stop for now and we're going to continue.